Good morning, dear participants. I warmly welcome you to the Day 6 program of the ITEC on the theme of energy systems and carbon neutral economy. We will be starting the first session for today, which will be on the topic from capturing carbon dioxide to its value addition, which will be delivered to us by Professor Vivek Polshettiwar. Dr. Vivek is an expert in advanced nanomaterials, nanocatalysis, and climate change. His nanocatalyst group is working in the area of nanomaterials, synthesis with control shape and morphology, and their application as nanocatalysts to tackle climate change. Dr. Vivek's final goal is to push the boundaries of catalyst research to develop nanocatalysts based on non-precious metals. He is also the recipient of prestigious Oak Ridge Institute for Science and Education Research Fellowship at the US EPA, as well as many other accolades to his name. So with this short introduction, I hand over the rest of the time to you, sir. Sir, you can start the session.
Yes. Good morning, everyone. Thank you for the invitation and thank you for the introduction. So let me share the slides. Can you confirm that the slides are playing and moving?
It is visible and it's playing as well.
Okay. So this is more like a workshop. So I will be in detail. I will be speaking in detail, and you can stop me at any time and ask the questions rather than waiting until the end of the talk. And today I'm going to talk about capturing the CO2 and also catalytically converting the CO2 into useful chemicals using a different catalyst, be photocatalyst or a thermal catalyst, using the work that we did recently from Overflow. We all know the CO2 is the main source for the global warming, which is changing the climate, which is one of the most serious problems mankind has ever faced. And there are several ways to combat the climate change. The best way is to stop using the fossil fuels, but we all know that is nearly impossible for next several decades. So we will be burning the fossil fuels, and if we continue doing that, we will be producing large amount of CO2. We will continue producing large amount of CO2. So that means one of the best way to contribute to tackle the climate change is capturing the CO2 from the environment, from the source from where the CO2 is emitted by different industries. And we also know that simply capturing and storage of the CO2 is also not the permanent solution. We really need to use that CO2, utilize that CO2 to make different chemicals that we use every day, that we need every day. So it has to be carbon capture, because capture is the first step to even further conversion, and then converting the captured CO2 into useful chemicals and fuels. So the capture and utilization of carbon dioxide should become the preferred path to manufacture chemicals and fuels. So CO2 should become our carbon source rather than the challenge that we face right now. And in my talk, I will show you some of the examples how we do that in our lab, how we are attempting to do that. So the simple solution is to stop using the carbon-based fuels, coal, gases, oils. But even now, the 70% of at least India's energy is coming from the carbon-based fuels, and that's why we're emitting large amount of CO2. So, and this situation is not going to change very quickly. It is going to, CO2 emission is going to increase because our population is increasing, and more industrialization, more and more process development. So we definitely need to move from the fossil fuels to renewable resources like solar energy, wind, and that is happening. But this alone will not, I personally feel that will not solve the problem. That will not allow us to achieve the net zero. You definitely need carbon capture and utilization. If one asks the question, what are the challenges of 21st century? Then CO2 is the challenge. Haber-Bosch ammonia synthesis was the achievement of 20th century. Because of the Haber-Bosch process, we were able to, provide the food to large number of population. Because of the ammonia synthesis, ammonia gave us different fertilizers that increases the productivity, and we got good amount of food, and that increases the population. And now the Haber-Bosch process alone, produces around 1% of the global CO2. Emits around 1% of the global CO2, but it also takes large amount of energy. So energy as well as the CO2 emission from the Haber-Bosch is one of the example of the 21st century challenge. Obviously, we all know the majority of the industries emits the CO2. Steel, concrete, the cement, they are the main emitter. But we also know that we cannot live without steel, without concrete, cement. We need all of that. Then again, if you look at the solution is either I produce the steel without emitting the CO2, or either I produce the cement without emitting the CO2, which is again seems not possible, although you can reduce the CO2 emission by developing the processes to make the steel or cement. But then if we can develop a process which will efficiently allow us to capture the CO2, and then if we can again do a value addition by converting that CO2 into useful chemicals, then again CCU seems to be the playing the bigger role in combating the climate change. This is typical thing that I kept showing to everyone, at least in the students, that this is a typical habit of Indian science and technology, that we think that everything will be developed, research and developed outside in other part of the world, and then we import oil, we import solar panels, batteries, and then we lose lots of our economy to them. But now I think this should not happen for the CO2 capture and conversion technology, right? And we should develop our own technology. We should invent and make that in India. Now, CO2 conversion is the most challenging process. The reason is CO2 is a very stable molecule, is a sp hybridized linear molecule. So if you want to convert CO2 into any useful chemicals by reacting with, say, hydrogen, alkenes, epoxide amines, and convert into alcohols, acids, then you will see you need huge amount of energy. You have a huge energy barrier that you have to cross over. That means I need to put in lots of energy to convert CO2 into useful chemicals. So there is an energy penalty if I convert CO2 into useful chemicals. But we have to, right, irrespective of the energy penalty, we need to capture the CO2. But then, how do I tackle the issue of energy penalty? And that can come from the solar energy, right? So if I can carry out the CO2 conversion using solar energy, then ideally this process could be sustainable, right? And again, there could be various ways of using the solar energy. It could be directly the solar photon. You do a photocatalysis, convert CO2 into useful chemicals. It could be photon to electrons, the electricity, and then you use electrochemistry, electrocatalysis to convert CO2 into different products. Or it could be a solar photon into a thermal energy, heat, and I do a conventional thermal catalysis to convert CO2 into useful chemicals. And it could be the combination of any of these, right? Photothermal, photoelectrochemistry, or even the thermal electrochemistry. And this is what is explored currently to achieve a sustainable process, which allows you to convert CO2 into useful chemicals. So in my today's talk, I will talk about first how to capture the CO2 from the point source, even before it's released, in the sense that if the CO2 is produced in the reactor inside, why do I wait until the CO2 comes out of the chimney? Like, can I capture the CO2 inside the reactor? We'll try to explain the challenges and possible solutions. Then I will talk about the development of black gold, which is a photocatalytic material, has the ability to harvest the solar energy at the same time convert CO2 into useful chemicals. And then I will talk about converting CO2 to different chemicals without any energy, without any external energy. The energy that is there in the reaction itself is enough to convert CO2. Okay, so I will talk about the advantage and what are the challenges of this particular process. Then I will, if time permits, I will talk about solid acids This is more for CO2 to DME and waste plastic to chemicals. And also a unique example of creating the defects in the material. We generally try to make a material which is defect-free, but we showed that one can create defects in the nanomaterial, and that allows you to then again catalytically convert CO2 into, say, methane, which is a green fuel if we convert from the CO2. So either I want to develop CO2 capture solvent or a CO2 catalytic material. One thing that you need, whether it's a catalyst or a CO2 solvent, one thing that you need is a high surface area porous material. And that high surface area can be utilized to, create active sites, which will either capture the CO2, say amines CO2 acid-base reaction and capture the CO2, or you can create some sort of catalytic sites onto the surface, which will then catalytically convert CO2 into, say, methane, methanol, ethanol, formic acid, into different chemicals that you require. So you need a high surface area material. And in our lab, we developed this dendritic fibrous nanosilica, DFNS, which is a pure silica at a nano size, or particle size from 50 nanometer to 1200 nanometer. That means I can make 50 nanometer particle, 100 nanometer, 200 nanometer, certain particle ranges. And it has a very high surface area, 500 to 1200 meters per gram. For those who don't appreciate the surface area numbers as such, the 500 meters per gram is like, this is the powder material. So if I take a 1 gram powder in my hand, it has like 1 football ground surface area. So you can use that huge surface area to carry out different functions. Could be a CO2 capture, could be catalysis, and there are several other applications of this material. And they have nice inherent properties like thermal stability. They are stable up to 800 degrees Celsius. Mechanical stability. They are stable up to 130 megapascal pressure. So that means I can use these materials to carry out high temperature reaction, high pressure reactions processes. And it's easy to synthesize. In fact, you read this Nature Protocol 2019 paper, we have given a stepwise detailed synthesis, including the videos, and anyone can make it at a larger scale. So this is how they look like, monodispersed spherical particles. And when you zoom in, you see these fibers. These are more like petals of the flower. At the nano scale, they are fibers. Then we try to ask the question in our lab that why we got a fibrous sphere, not some other shape or structure. And to understand the permission mechanism of this fibrous sphere, we need to understand how we synthesize. So we use this template molecule, which is CTAB. You have the C16 cetyl group, which is a non-polar, and then you have this quaternary nitrogen as a polar group. And we know these are the surfactant molecules. When you add them into some solvent, they form the micelles. Right, so when we added the CTAB into a mixture of water and xylene, polar non-polar solvent mixture, then and the concentration of the CTAB was such that it forms the lamellar micelles, and they further undergo a rearrangement to form these droplets, and, and these droplets are the template. I will show you the animation to understand this better. So these are the CTAB molecule. Blue ball is this quaternary nitrogen. That exact line is the C16 acetyl group. And then when you add them into a solvent, our solvent is water xylene. And the concentration of the CTAB is such that they form these lamellar phases. And once they form the lamellar phases, we added one more co-surfactant, say pentanol or hexanol. They will go in between these quaternary nitrogen, minimize the repulsion between them, and that stabilizes these interfaces. And what we observe that these lamellar phases are not floating flat into the solvent, but they are in the form of a microemulsion droplet, bicontinuous microemulsion droplet, because we have xylene and water trying to continuously mix. And these bicontinuous microemulsion droplet, BMDs, are just made up of water, xylene, and CTAB. So these are the template. These are the nano template. And in the channels, in the water channel, I have a silica precursor, which will then hydrolyze, condense, and form the silica within the channels. So the channel length, channel width will decide the thickness of the fiber, and the overall size of these droplets will decide the overall size of the DFNS particle. You keep them away, you get a very small particles. And we also learn how to merge them together without really destroying their internal organization arrangement. And if you merge them, then you get a bigger droplet, bigger BMDs, and you get a bigger silica nanoparticles, DFNS nanoparticles. So that's how we were able to tune the particle size from say 50 nanometer to up to 1200 nanometer by simply changing some of the reaction conditions. Okay, so this is our material. We have several patents on it, and now more than 150 groups are using it for large number of applications: catalysis, CO2 mitigation, drug delivery, sensor, energy storage, energy harvesting. So it's ideally it's a silica, but then we have ability to then functionalize this material. You can make it hydrophobic, you can make it hydrophilic, you can make it semiconducting by coating with some semiconducting material, even a plasmonic by coating some plasmonic material. You can load the drugs. So you see a huge number of reports of the utilization of this material for a range of different applications. We are only our focus is always on CO2 mitigation, CO2 capture, and then catalytic application. Sorry for that. Okay, so now we use that silica material to then develop a CO2 solvent. So now developing the CO2 solvent, to capture the CO2 is the easy part. Conversion is the difficult part. So it's a simple acid-base chemistry. If I create a basic sites onto the surface, then done, right? It's amines. If you can deposit the amines on the silica surface, they will capture the CO2. And they generally do that, say around 75 degrees Celsius, 50 degrees Celsius, up to 100 degrees Celsius. And that's called the post-combustion CO2 capture. I'm not showing those results. I'm showing something else, which is, can I capture the CO2 even before it gets released into the environment, even before it comes out of the chimney of the industry? Means where the CO2 is produced. Say if I'm doing a Haber-Bosch synthesis, then within the reactor the CO2 is produced. So can I capture that CO2 within the reactor so that it is concentrated, easy to capture? Not easy to capture, but it is concentrated there. So once it comes to out of the chimney, it will get diluted. And more the dilute CO2, you will have challenges to capture it, like direct CO2 capture. Now, most of these processes, like Haber-Bosch, steel, cement, all of these processes works at very high temperature, 500 to 700 degrees Celsius. Could be different temperatures. So I need to have a material, a CO2 sorbent material, which is stable at that temperature and which has ability to capture the CO2 at that temperature. Right? Amines will definitely not do it. Amines will just degrade at that temperature and everything will be solid. But there is one material which is known as lithium silicate, which is stable at that temperature and has the ability to capture the CO2. And how it captures the CO2? You see, this is a typical reaction. So it's a chemical reaction of lithium silicate, Li4, SiO4 with CO2 to get you Li2SiO3, that is lithium orthosilicate. So this is lithium silicate and this is lithium orthosilicate, Li2, plus lithium carbon. And this reaction is reversible. So if I change the if I change the gas from CO2 to nitrogen, this reaction goes reversible, and then you produce the CO2 that you can just store somewhere. Now the challenges are, you really need the lithium silicate to capture large amount of CO2, and that to be at elevated temperatures, say 500 to 700. For any CO2 capture sorbent, the rate of absorption and the desorption should be fast, and they should be stable. They should show hundreds and hundreds of cyclic stability at that high temperature. So that seems to be very challenging. But then we thought of our hypothesis was we use the DFNS and convert that DFNS silica into lithium silicate nano. Ideally, we started with nanospheres, but we were not ever able to stop the reaction at nanosphere scale, and these nanospheres broken down into nanosheets. So then we decided to convert these into nanosheets of lithium silicates and explore them for CO2 capture at high temperature. So this is how we prepared a simple synthesis: DFNS, lithium nitrate, 650 degrees Celsius for 6 hours, a solid phase reaction, and you get lithium silicate. When we did the PXRD, you see most of the deflection pattern signals are for lithium silicate. There is some impurity of lithium orthosilicate and lithium carbonate. And this is because while we are heating in air has this 400 ppm CO2. So as soon as lithium silicate forms, it starts capturing that air CO2 in the air and start reacting with that air. And that's why you got a lithium orthosilicate and lithium carbonate while doing synthesis. We were able to remove these if I do a synthesis in inert atmosphere, and you get a more than 99% pure lithium 4 SiO4. But we decided not to use the inert atmosphere because then again its process will become less sustainable. We said, okay, it's okay to have some amount of impurity if I still able to get a good amount of CO2 capture using such a say it's 90% pure material. Surface area was no good, but here it's more a reaction. It's more a molecular reaction of lithium Li4SiO4 with the CO2. So surface area should not matter much. And then we carried out the CO2 capture studies. So you treat the surface with inert gas to remove some adsorbed chemicals and moisture, and then you expose the material with CO2, and then see this is done in a thermogravimetric way. So you put the material here in a balance. Your solvent, you will have a empty sample holder as a reference, and this entire thing goes inside the furnace, and this is where the gas is coming, the CO2 is coming. So if this material captures the CO2, then there will be wet gain, right? And by just knowing the wet gain, you can find out the CO2 capture capacity, kinetics, and other properties. So this is how it is. So we started flowing the CO2, and we started monitoring the wet gain, which is due to the CO2 capture by the material. And you see in first cycle, there is some CO2 capture, say around 20% in 40 minutes. And then interestingly, second cycle, it captures more CO2. Third cycle, it captures even more. And fourth cycle, it captures maximum amount of CO2. And it also changes the kinetics of the. So somehow during the adsorption-desorption cycle, the material's property is changing, and material becomes the most optimized at fourth cycle. Afterwards, it was not changing. And not only the CO2 capture capacity, which is to reach around 32, 33 wet%, but also the CO2 capture kinetics also change. You see, first cycle, it was 6 wet% per minute, then it will be 14, say 19, 21, and it remains there. So both the things are changing. And then we ask the question that what could be the reason for such a change in capture capacity with the cycles. For that, we then studied the material after fourth cycle. And what we observed that after the fourth cycle, the impurity that we had, lithium orthosilicate and lithium carbonate, that reduces, because now the desorption is happening in nitrogen environment. So because that means you are purifying the material up to the fourth cycle, and now there you have a most purified lithium 4 SiO4 phase, and that's why they are capturing a good amount of CO2 and better kinetics. And XPS also shows the same thing, that you get a more purified version of fourth cycle. And if you compare our material with any other material reported until we publish the paper, you see most of the other material loses their stability in less than 30 cycles, but whereas ours is very stable. Now one can ask this question that lithium silicate has lithium, and therefore ideally this is unstable, unsustainable process. We know the challenges of lithium-ion battery. Everyone is trying to replace lithium by something else, something cheaper and easily available to make the lithium-ion battery sustainable. Exactly same thing can be said for this process, that it has a lithium, and therefore ideally this process is not sustainable. Agree, one can replace say lithium by sodium, potassium, magnesium, but lithium is lithium. None of this work. We tried sodium, potassium, because it's all about the mobility of the ion, and lithium is so small and highly mobile that it only works. Other material doesn't. Other one doesn't work. We are still trying to see the alternative, but you cannot really replace lithium right now by any of these metals. But then, is there any other way to make this process sustainable? And there could be one more way, which is I keep using lithium silicate for a large number of cycles. I'm not losing the lithium. Lithium is always there, right? I use 1 cycle, 2 cycle, 3 cycle. I use hundreds and hundreds of cycles to capture and dissolve the CO2. Then ideally this process can be sustainable. And that's what we observe, that we try to do this up to 200 cycles. Obviously, there's no limit, but 200 cycles means we need to use our instrument for around 3-4 weeks. And what we observe is you capture the up line is a capture, and then line which is coming down is a desorption. Adsorption, desorption, the fourth cycle it becomes stable, it reached that level, and then you see they looks exactly same. Obviously, when you zoom in, they are not exactly same, but they are nearly the same, around 35% weight% of CO2 capture up to 200 cycles. So there was no significant change, very minor change if you zoom in. So that clearly indicates that this material can be used for a large number of cycles, and therefore this process could be sustainable. Then the other question that we ask is why our material is better than the conventional materials. And there we propose this mechanism, a new mechanism. In general, the conventional material, when they react with lithium silicate, when CO2 reacts with lithium silicate, they form some sort of a core shell model, double shell model, where you have lithium orthosilicate at the core and lithium carbonate at the shell. Now, when you want to reverse this reaction, right, in a desorption step, you have to react this lithium carbonate with a lithium orthosilicate. And you can imagine that at the surface, at the interface, the reaction could be efficient, but at the center, more the deeper you go, the reaction will not be efficient. And that's why desorption is always incomplete. So every time you capture and desorb, the desorption is incomplete. So with few cycles, you will never able to then desorb, you will never them to react with each other, never able to get back the lithium for SiO4. Whereas in our case, we propose a mixed phase model because of the nanosheets nature of the material. We have some sort of a mixed phase model where you have a mixed phase of lithium Li2CO3 and the white Li2SiO3. And now you can see when you do a reverse reaction, when you do a resorption, their reaction with each other will be more efficient because now they are mixed with each other. And that's why we were able to desorb entire CO2, 100% desorption, because of the efficient interaction between lithium carbonate and lithium orthosilicate. And that was the reason why our lithium silicate nanosheets were better than the conventional material. This is not hypothetical, but we then proved this by using the exposed depth profiling. So if this is true, then if I take the lithium silicate, the nanosheet that we prepared, and capture the CO2, then they should form the lithium carbonate and lithium orthosilicate. And if this is a mixed phase, then if I slice the surface at different depths, say 0 nanometer, 70 nanometer, 34, 51, 68, then at any depth, you should always see both the phases. Then we can say it's a mixed phase. If one phase is more than the other, then it should be a double shell model, right? If I slice here, then I will only see a lithium orthosilicate, right? If I slice at the top, I will see only lithium carbonate. Whereas in this case, at any depth you slice, you will always see the mixed phase. And that's what we see. At any depth we slice, we always have the mixed phase. Obviously, they are not perfectly 50-50%, which is normal, right? Because this is a cartoon, and in reality, it cannot be so perfect. But they are still there. Both the phases are there. They are mixed. So this clearly indicates that our mixed phase model is working, and that's why you got a better adsorption-desorption kinetics. Okay, so this was another material that we prepared where we took the same DFNS, functionalized with amine, and we were able to capture the CO2 that is coming from the chimney. So this is post-combustion CO2. The other one, the previous lithium silicate, is a pre-combustion CO2. Capture the CO2 within the reactor. This one I'm not presenting. So now we all know the CO2 capture is not the solution, right? Conversion is the best solution. So I will show you some of the examples where we converted the CO2 to fuel at the same time we used the solar energy. So the idea was, can we develop a material which not only capture and activate the CO2 catalytically, but can also harvest the solar energy. So you have an energy harvester and a catalytic material in one material, one hybrid material, which will do both the job. And we wanted to use the SPR, surface plasma resonance property of a gold to achieve this. We all know that gold is shiny yellow when it is bulk, but when you go to different nanoscale sizes, you get a different. But the reason is the electron cloud on the gold nanoparticle resonate with the electric field of the light, and depends on the size, depends on the electron cloud, it will resonate at different wavelength of the light, and then that wavelength, that light will get absorbed and that's why you get a different color. That's the surface plasmon resonance. So we wanted to use this particular technique to carry out the catalysis, to carry out the CO2 conversion. Maybe I will explain this in a bit detail. So once the surface plasmon resonance takes place, there is a damping of the SPR, and all that energy get absorbed and damped onto the surface of the material, surface of the nanoparticle. And that energy is then used for excitation of the electron from, say, S to S or from D to S transition. And obviously D to S transition is preferred because of the longer lifetime. Now these electrons, which are above the Fermi level, these are called hot electrons or excited electrons, can be then injected into the CO2 molecules, right? And then I can activate the CO2 because now it is a CO2 radical anion, which is more reactive than the non-neutral CO2, and I can convert that CO2 to glutamate. However, the lifetime of these electrons are extremely short, few femtoseconds. Then, during the relaxation process, these hot electrons again undergo electron-electron collision with the electrons which are there in the Fermi level, and they form this some sort of a secondary population of hot electrons. These are called the Fermi-Dirac distribution of energetic gas carriers with a better lifetime, and these can at least be used to again inject into the CO2. If we even miss these electrons, then there is this electron-phonon coupling, by which all that energy that was absorbed, the photon energy, sun energy, will get converted into heat by electron-phonon coupling, localized heat onto the surface. And if you have the surface with the catalytic sites and the CO2 sitting there, then you can ideally carry out a thermal reaction, conventional thermal reaction using this localized heat. So we wanted to use all these aspects of plasmonics to carry out catalysis. Now, if I just take a gold nanoparticle and put it on a silica, then the light absorption behavior is something like this: a blue color. It absorbs around 550, and then the weak absorption in other part of the solar spectrum. If you really want to develop a good catalyst, then I really need to develop a material which harvests entire solar spectrum, visible and even near IR, a broadband light absorption. How do I do that? So there are two ways of doing it. One is called by playing with the particle size. If I change the particle size, you can see now the lambda max is changing from say here 500 nanometer. So now you can go to 600 nanometer. But again, it's the lambda max which is changing. It's not getting really broadened. It's shifting from one wavelength to another. We really wanted a broadband light absorption. And there is another concept. It is called the plasmonic coupling. So when you bring these gold nanoparticles closer and closer, their electron clouds start interacting, right? And that's called the plasmonic coupling, which allows you, based on the distance between them, based on the gap between them, that allows you to have a broadband light absorption. So we wanted to use these two concepts and see we can develop a material which harvests entire solar spectrum in the visible and near IR light. Now the challenge is, how do I, play with the gaps of the nanoparticle? I can easily play with the nanoparticle sizes, but what about the gaps? How do I do that onto the solid surface? So there we came up with this hypothesis that silica sphere has a lot of these fibers, silica sheets. So we will coat these silica sheets with the small gold nanoparticles, create some sort of C0, and then in the next cycle, we will only grow the existing gold nanoparticle without creating any new nanoparticle on the silica sheet. So because now the particles are growing and growing, you see they are coming closer and closer, right? So we were able to achieve two things, like heterogeneity in the particle size, allow you to get a broadening light absorption. At the same time, the gaps between nanoparticles also change, and they are coming closer and closer. And so that's why we prepare different samples, because we don't know what is the optimized gap that is required to have a better light absorption when we started the project. So we decided to make different material with different gaps and find out which one has a better ability to harvest the solar light. And these are the TM images. You see C0, C1, C3, C4, C6, and you see here the particles are getting crowded, right? They're coming closer, and say in C6, they started connecting. We don't want the particle to connect. We wanted to have gaps between them where you create these hotspots, electrical hotspot and thermal hotspot. And if your reactor molecule, the CO2, is in that thermal hotspot, it will experience that electric field thermal energy, and that will help us to then reduce the activation energy barrier of those molecules and possibly to carry out the reaction at a lower temperature or only with the light. Right. And now you see when we made this material, the gold becomes black gold. It's still a metallic gold, no change in oxidation state, there is no doping, there is no functionalization. But it's simply the gaps between the particles are different, which allowed the plasmonic coupling, and that allowed them to then absorb, see now the light absorption behavior of these materials. Just like this, and they slowly becomes broad, and you started absorbing entire visible and near light. So more the photon you absorb, you will create more hot electrons, which can then be used for catalysis. Or those more hot electrons will go under electron phonon coupling, and you will get large amount of localized heat, and then you can do a conventional catalysis, or both of them, combination of them. Now, in order to understand the heat produced, right? Once the hot electron is produced, those undergo electron phonon coupling, and we wanted to know the localized heat, the temperature of the surface. So the simple experiment that we did is we put these black gold into the water, exposed with light, and see whether we can heat the water. What we observed that C4, cycle 4, heats the water in say 7 to 8 minutes, around 90 degrees Celsius. So clearly C4 seems to be the best material in terms of the gaps between the gold nanoparticle. Okay, but the only drawback of this experiment is here we are measuring the temperature of the water. So that means heat is produced onto the gold surface, and that heat transfer from the surface to the water molecule, and then water molecule to the environment around. So there is lots of heat loss. So whatever the temperature that you see of water may not be the surface temperature. So in order to really get the information of the surface temperature of the black gold, we use the Raman thermometry, which is based on Stokes and anti-Stokes cells. We know that when the molecule is is heated, you will have more population in a higher vibrational states, right? So here you can see more population is more in the higher vibrational states. So you will get more anti-Stokes lines as compared to the Stokes lines. So by just knowing the ratio of anti-Stokes versus Stokes line, you can get the surface temperature T of the material, right? So using this particular equation, we were able to calculate or measure the surface temperature, and we observe that one can go up to 150 degrees Celsius. There is an error bar, but it's still 100 to 150 degrees Celsius surface temperature, which is again indicative, because if I change the laser power, the light wavelength, again you may get a different surface temperature. But this at least indicate that one can get a very high temperature by simply exposing the black gold with light. Skip this part, and yeah, and then we did the photocatalytic CO2 conversion to methane. So it's a CO2 plus water, and you see DPCCX is the dendritic plasmonic polydrosome, which is your black gold, and visible near air is your sunlight. So black gold, sunlight, water, and CO2 your methane, and it's around 1.5 micromole per gram. If I compare this same reaction with a normal gold particle, then this is 10 times less. So we got around 10 times more, a better catalytic activity of CO2 conversion to methane. Right. So that way it really indicates that the plasmonic coupling and black gold works better. However, if one really look into the values of y-axis, it's only 1.5 micromole per gram, right? So it's too low for a commercial application of this system. It need to be there need to be a dramatic increase in the methane yield, and we know the reason, and we're working on this project now. We know the reason. Reason is the lifetime of the hot electrons in the black gold is really short, so we're not able to really transfer those electrons into the CO2, and that's why we're not getting methane, right? But now we have another work going on where we were able to convert large amount of CO2 in methane by simply increasing the lifetime of those electrons, which I will show you in some of the future talks. So I told you the advantage, and I also told you the disadvantage. But if one day we make this really sustainable with these values, say in moles per gram, in very fast kinetics, then something like this is very much possible. You have these reactor in your car, and we expose with light, sunlight, and then CO2, water, sunlight, get methane. Methane is your CNG, green methane, convert into energy, drive the car, and the CO2 that is burned out from the methane again goes back to the same catalytic reactor, and you create some sort of a cyclic process. Right? For this to happen, we really need to develop extremely efficient catalyst, which is still not there, and this is where everyone is trying to work on. Okay, so this was published in Chemical Science and came up with this cartoon. Okay, any question if you have until now I can answer before I jump to the next topic.
No question, sir.
Hello.
No question, sir.
Okay, so we will go ahead. So this work looks interesting because it works using the solar light, but the challenge is not only the activity, not only the productivity of methane, but also the use of gold, right? Gold is expensive. Why do I use a gold to solve such a huge CO2 problem, right? There's already a gold rush in this country. So can I replace gold with something else? Or can I use a very cheap material? Something like this, a sand on the beach, which is everywhere, right? You go anywhere, you find the sand. So can sand on the beach convert CO2 to methane, right? So that's the question that we ask. And when I look at sand, it's nothing but a silica. It's a CO, it's SiO2, right? So we first thought, okay, let us convert the sand into nanosilica, right? So and see whether that works. Obviously, it doesn't because SiO2 is a very neutral molecule. What can be done to really activate the sand, activate the SiO2, so that they can activate CO2 and convert it to methane? That's the question that we ask. And the reason for that is if we look at the CO2 plus hydrogen to get you methane, CO2 methanation reaction, almost all the catalysts are metal-based. Although they are extremely good, they have an issue with the stability. They oxidize, they undergo sintering, and you lose the catalytic activity of these materials. So therefore, if we replace the metal with some non-metal, something else, if there is no metal, then the issue of stability just goes away. So that's where we then came up with this idea that I create the defects in the material, and possibly those defects will activate the CO2. So this is how the silica looks like. Silica is amorphous SiO network. So if I break this bond, OSI bond, right, then I will get O radical and Si radical. Si radical in literature is known as E centers, and O radical is known as non-bridging oxygen hole center. Because I broke this bridge, this is a non-bridging oxygen hole center. So I will just say O radical, Si radical to simplify our understanding. If I break this bond again, then that oxygen will go away, and I get two Si radicals shown here, and you have this oxygen vacancy, right? There is no oxygen, so that's oxygen vacancy shown here. So I can create Si radical, I can create oxygen radical, and I can create oxygen vacancies. And oxygen vacancies is known as oxygen deficient center, ODC. I will use the word oxygen vacancies. So we ask two questions. One, how do I create these defects artificially? And how do I tune their types, tune their concentration? That's the first synthetic challenge. And then whether these centers really activate CO2, really dissociate hydrogen. And this is the work that we recently carried out. It was one of my master students, and where we showed that yes, it is possible to create the defects, create these imperfections, and you can perfect these imperfection by creating a perfect concentration of and type of these defects, and that does allow you to convert CO2 to methane. How do we did that? So SiO2, there is this process called magnesiothermia, which means when I take a silica mixed with a magnesium, right, and so consider this a tube, a quartz tube, add a silica, add a magnesium, and evacuate the tube. There will be no oxygen. So you create oxygen-free environment in the tube, and you seal the tube. Now the tube only has magnesium and silica, SiO2 and magnesium, and there is no oxygen because it's under vacuum. And then you heat the tube, say around 675 degrees Celsius. So at that temperature, magnesium vapors will be in large concentration. And these magnesium vapors now needs oxygen. They want to react with oxygen and convert magnesium into magnesium oxide, more stable state. But since there is no oxygen in the tube, what will they do? They will take the oxygen from silica, from SiO-Si network. And based on the magnesium concentration, based on the temperature, based on the reaction time, you can selectively remove some of the oxygens so you keep breaking these SiO bonds. And based on the concentration of magnesium, you can tune the concentration of S radical, O radical, and the oxygen vacancy. This is exactly what we did. And we use 10 weight percent magnesium, 25 weight percent magnesium, and 50 weight percent magnesium to tune the defect concentration and their types. And this is how the samples look like. Silica is white in a visible light, blue in a UV light. And you see now they changes the color by treatment with 10 weight percent, 25 weight percent, and 50 weight percent magnesium, indicating at least qualitatively that there are different defects that is found. Now to understand what are those defects, we carried out the photoluminescence spectra, and you can see DFNS has this intense peak around 430 nanometer, which is for dioxocellerine and cellerine. But with treatment with the magnesium, that particular signal goes down. So see 10, 25, 50, those defects are gone. But around this range of 600 to 1030 nanometer, around 810 nanometer, you see a new additional signal here, which is for oxygen vacancy, which is for this non-bridging oxygen hole center, the O dot. So clearly DNS10 has the highest amount of O dot, then 25 and 50 don't have the O dot because large number of magnesium, so both the SiO bonds are broken and you got more Si radicals possibly. To see the Si radicals, we did the EPR study, which again shows that DNS10, 25 and 50, so 50 has more number of Si radicals, which is because now I'm broken down more and more oxygen SiO bonds, which is obvious. Then based on these preliminary characterization, we carried out the CO2 reduction. CO2 plus hydrogen get you methane, water, and there is small amount of CO produced. So now you mix CO2 and hydrogen, and this is your catalyst bed, which is heated at 400 degrees Celsius, 1 bar pressure, atmospheric pressure, and then we monitor the reaction using gas chromatography. So what you see is that when you create the defects in the silica, DNS10, 25, 50, you see there is increase in the yield of methane. And here the yield is very high, 3750 micromole per gram per hour. It's a good amount of yield. And we observe that DNS25 has the highest amount of yield. Somehow this material is better as compared to other. Then we ask the question that why DNS25 is better. Before that, we also did the stability study, and what we observed that in 24 hours, the activity decreases from say 3700 to around 3000. Not a huge decrease, but there is a decrease. And the question is, since there is no metal, why the activity is decreasing? Ideally, it should not decrease. So we thought it could be some amount of carbon formation. So let us burn the carbon away from the defect site, and ideally I should get same activity. Interestingly, every time we did this regeneration, which is like heating the catalyst at 550 degrees Celsius in air, aiming to burn the carbon, every time we do that, we observe an increase in the catalytic activity up to 7 cycles, right? And then they are nearly the same within the error bar. We have showed the error bar. And so that's another interesting question now, that why the activity is increasing every time I do the regeneration. Ideally, it should not. It should remain, say, around 3700. And that's the best we observe. So somehow we have 2 questions to answer: why DNS25 is best and why the activity is increasing. So DNS10 has highest amount of O centers. DNS50 has highest number of E centers. This is coming from PL, this is coming from EPR. However, it is DNS25 which shows the best activity, neither 10 nor 50. This clearly indicates that there is some sort of a cooperativity between O and Si radicals, and they need to be in a good concentration. It cannot be that one is higher and one is lower, and this guy is higher and this guy is lower. There need to be some optimized concentration, which is the case in case of DNS25. And that's why there is a cooperativity between these 2 centers, and that's the reason DNS25 is better. Regarding the why the catalytic activity increases with every cycle, what we observe that every time we do regeneration, we were able to increase the number of defect sites, E centers as well as the oxygen centers, up to 7 cycles, and that's why we were able to get more and more activity up to 7 cycles. And then they saturated. We then did lots of in situ studies to really understand how the CO2 interact with defect site, how the H2 interact with defect sites. I will not go into the details, but we also try to also trap some of the reaction intermediates so that we can come up with a mechanism. This is still a proposed mechanism. Some of the steps are known that we are still under investigation. But what we observe that CO2 get captured by interaction with these O radicals and the sedanols somewhere here, and then it undergoes several rearrangement of a monodentate and a bidentate carbonate, and here the CO get dissolved if it doesn't see the hydrogen. And at this stage, H2 get dissociated by the Si radicals, and one of the H get transferred to carbonyl, and you get a pre-carbonyl species. You add another hydrogen, you add another hydrogen. I'm not going into the details because this will take its own time. And then another hydrogen. So if you add 4 hydrogen, I get a methane. And by simply heating, you can regenerate these defect site, and this cycle again and continues. Okay, so I finished nearly 1 hour. So how much time I have? So I prefer to have some discussion rather than I keep speaking. So it's 9:30 to 11. So it's 10:21. Maybe I will show you one more data, and then I will end. And maybe if you have a question, then we can discuss that. So the third project that I will show you, for that I would like to ask this question. This is very debatable thing, that is CO2 capture and conversion really a solution for stopping climate change? Because we have a huge amount of CO2, and the amount of CO2 that we are able to capture and convert is not that high, right? So is it really possible? Now, the answer to that question could be another question. What could be the dream process for CO2 conversion? The dream process could be that you should able to convert the CO2 to useful chemicals, like say methane or methanol or something else, at ambient temperature and pressure. That means you don't need to really think about energy for that. Without any extra energy, no electricity, no solar energy, no heat. Whatever the energy that is there during the reaction at room temperature, it should be enough to carry out that reaction. And then water as a hydrogen source. I don't need to really look for the hydrogen for somewhere else. Can I use water directly as a hydrogen source? And somehow water produces the hydrogen during the reaction and react with the CO2. And the most important, entire these things should happen with inexpensive and abundant material, not gold, not silver, not ruthenium or rhodium. Those are all expensive, very limited resources. Can I think of something which is extremely inexpensive and abundant in material? And this is what we found very recently, where we observe that CO2 reacts with water in presence of magnesium at room temperature and even below the room temperature. It gives you methane, methanol, formic acid, and hydrogen, and basic magnesium basic carbonate. Works at room temperature and atmospheric pressure, don't need any light, any electricity, any heat. Energy that is there in the reaction vessel is enough to carry out that reaction. And it's just using the water, no external hydrogen. And even that water doesn't need to be pure water. Even seawater works. Even seawater works better than the normal water. Magnesium is the fourth most common element in the earth, after iron, oxygen, and silicon, making 30% of the earth. These are some of the catalytic results. You see, in less than 10 minutes, I will able to produce, say, around 100 micromole per gram of CO2 after methane from CO2 at room temperature, atmospheric pressure. So this is a very good number. Not only the pure CO2, even I take air, which has around 400 ppm CO2, we were able to convert all that CO2 into methane. Right? So it's only 3 micromole per gram because you only have 400 ppm CO2 in the air. But even direct air capture is possible at room temperature, right? Using simply water and magnesium, no other hydrogen source. We did study other metals and the bimetallic version, but we at the end observed that it is the magnesium which has the ability to do this in more efficiently. We also then, as usual, try to study the reaction mechanism using in situ IR and the dip studies, ATR, FTIR studies, which I'm skipping. And then we propose this particular mechanism where magnesium reacts with CO2 and water produces this basic carbonate and the hydrogen. And then it forms the cyclic carbonate. It gets the electron from magnesium, proton from water, and creates some sort of intermediate 3, which again gets the electron from magnesium, proton from water. And you keep adding that, you get a formic acid. If you keep adding more and more electron and proton, you get methanol. And if you add more electron and proton, you get methane. And we observe methane in a large quantity. Now, whether the process is sustainable, what is the catch? So, if we calculate the sustainability, 1 kg of magnesium produces 2.43 liters of methane, 940 liters of hydrogen, and 3.85 kg of magnesium basic carbonate. And that is the drawback. This magnesium is so reactive that once this reaction is completed, magnesium reacts with water and CO2 and produces magnesium basic carbonate. And then this becomes non-catalytic at the end of the reaction. So this process, so you're losing the magnesium in the form of a magnesium basic carbonate. And that is the challenge of this process. However, how do I solve the sustainability issue? The magnesium basic carbonate itself has lots of use. It can be used as a green cement, can be used as a pharmaceuticals, flame retardant, a large number of applications. So even if the process is non-catalytic, because of the use of magnesium basic carbonate, the process could be sustainable. Right, and at least in India, we have a huge amount of magnesium ores, and we don't need to really depend on some other country to produce the magnesium for us. And if we look at the price, the magnesium is very cheap. So there are different prices on website. I took 700 rupees a kg, and if and the magnesium basic carbonate, which is available only at a research quantity, is very expensive. It's 2,000 to 5,000 rupees a kg. I took 2,000 rupees a kg price. And if I do a calculation, 1 kg of magnesium costs you 700 rupees. It produces 3.85 kg of basic magnesium carbonate. I mean, just ignoring methane and hydrogen. They are priceless, right? You cannot really compare the price of green methane and green hydrogen with the normal methane and normal hydrogen, which are very cheap. But even looking at magnesium and magnesium basic carbonate, you see the business is profitable, right? So clearly this is economically viable. Only challenge that now you have is the magnesium that is produced conventionally emits good amount of CO2. However, if I produce the magnesium using, say, a magnesium chloride or a magnesium silicate instead of conventional magnesium carbonate, of course, then CO2 emission will be nearly zero. Not be zero, but nearly zero. Also, the energy required for converting those chloride and magnesium chloride into magnesium, if that energy can come from the solar energy, then energy penalty also becomes zero. Right now, you have 18.8 millijoules of energy. So if we solve these two challenges, then this process looks like a dream process, right? In addition to a magnesium basic carbonate, you can also think of producing the hydrogen using this method. You see here, if I react magnesium with water alone, you get only 2.24 liters of hydrogen per kg of magnesium. However, if I react the magnesium with water in presence of CO2, I am getting huge amount of hydrogen, which is 420 times more than the hydrogen produced this way. And then the ideal scenario could be that I have some sort of a cartridge filled with a magnesium powder, and then one is a water, another is CO2 chamber. You mix them and pass through the magnesium cartridge, and based on the flow of water and CO2, you will be able to tune the flow of hydrogen. So it's like you can produce the hydrogen on demand. You don't need to really produce a store. So you just store the magnesium powder, water, and CO2 cylinder in some compact instrument and create the hydrogen on demand. This is another application that we're thinking about. And this is more futuristic, but you never know. There is a recent discovery in Nature Geoscience which says that Mars has huge amount of magnesium. And we all know that Mars also has the CO2 and water. So you have water, you have CO2, you have magnesium, and there is the solar energy to convert these magnesium to magnesium zero. And ideally, you can then use this process even at Mars. Maybe it's too futuristic, but you never know. Okay, so this way, I try to stop here and have a discussion if you want. So there are some other work that we did, where we developed the material for degrading plastic into chemicals, which I will skip for now. So today I showed you a new material, dendritic fibrous nanosilica, a high surface area material that can be used to develop the CO2 solvent as well as a catalyst to convert CO2 into chemicals. I also showed you lithium silicate nanosheets, which allows you to capture the CO2 at a very high temperature, and they showed a very good stability. Then I showed you a magnesium process where the magnesium and CO2 and water reacts at room temperature and converts into useful chemicals, including methane and green cement. I also showed you the black gold work where we tune the particle distance between the gold nanoparticle, which allows the material to lack and absorb entire visible to near IR light. And you can use that light absorption behavior, those hot electrons and localized heating to do a catalytic CO2 conversion. And I also showed you the creation of defects in the nanosilica, sand to nanosilica, and how to explain how to create the defects, how to tune the defects types and concentration, and that allowed us to then activate the CO2 and hydrogen and convert CO2 into methane. With that, I like to thank Department of Atomic Energy, who gives us the majority of the funding, then Indo-French CEPIFRA project, Shell Industries, DST Mission Innovation, BASF, and Hindustan Petroleum for funding. Professor Ayan Datta, Professor Deep Chakraborty, and Professor Oliver Lefon for collaboration for solution NMR and computational support. And this is my group, Sushma Rao, Anmati, Rajesh Belgamwar, Saidip Singh, Sushma Kundu, and Rishi Verma, who carried out some of these works. And with that, I'd like to thank you very much, and I'm more than happy to answer the questions. You can unmute yourself and ask. Don't hesitate, I guess.
Dear participants, you can, if you have any queries, you can take the time to ask Professor. And if there is a chat box given, so there also you can post your questions.
Yes.
Thank you.
Okay, if there are no questions, then we can end here, right?
Yes, sir. Sir, thank you very much for the very informative and insightful presentation. I believe all the participants will be taking this learning into their respective fields. And sir, we truly appreciate your time here with us today. Thank you so much, sir.
Thank you, and bye-bye, everyone.
Bye, sir.
Thank you so much, sir.
Bye-bye.